This is the same image we looked at to start the Inner Planets lecture. It bears repeating simply because it illustrates that one of the major differences between the inner terrestrial planets and the outer gas and ice giants is size. Here you see the outer planets plus Pluto. We'll get to Pluto in the next lecture on solar system debris. The outer planets are often called the gas giants, principally because they have extremely deep atmospheres due to their strong gravitational pull. They probably have a solid core somewhere below, but those cores have never been directly observed or measured. Notice just how much Uranus is tilted over 90 degrees so that it looks like it's rolling rather than spinning. This is probably as a result of a massive collision. Pluto has a similar tilt. You can also see that each of the outer planets has a magnetic field similar to that of the Earth. The magnetic fields of Jupiter and Saturn are like Earth's, but are much stronger. Notice that Uranus and Neptune have magnetic fields, but they don't line up very symmetrically to their axis of rotation. Jupiter is an enormous planet. Here you see the banding structures in the atmosphere. If you Google an animation of Jupiter, you'll see that some of these stripes travel toward the left, while other bands travel toward the right. You can also see the shadow of a moon passing over the giant planet. Earth's moon is pretty large. It's about 27% the size of Earth's diameter. Jupiter's moons are dwarfed by the size of their parent planet, at only about 2% of Jupiter's diameter. Here's an image of Jupiter and its great red spot as taken from the Voyager spacecraft. Jupiter is primarily made of hydrogen and helium like the Sun. Jupiter, though, is much less massive than the Sun and is not capable of igniting like the Sun did. The current moon total is, at the time of this recording, about 100, having been recently increased due to the defining of the orbits of additional objects. This number will continue to change over time as new objects are discovered. Jupiter is so large that 11 Earths could fit across its diameter. It's 300 times more massive than the Earth, and you would weigh more than twice as much on Jupiter as you do on Earth. There's a relationship between a planet's mass and its radius that determines the gravitational pull you feel on a planet. Even so, remember that Jupiter is a gas giant, so even though we can measure what you would feel as weight on that planet, you couldn't actually walk around on it. You'd simply begin falling through the gas until you were crushed by the pressure of the atmosphere on top of you. Jupiter is basically a space vacuum. We here on Earth may owe our existence to massive Jupiter protecting us from rogue bodies flying through the solar system. In this image, can you see the dark spots in a line across Jupiter? These marks resulted from a comet that flew too close to Jupiter. The giant planet's gravity pulled the comet apart, and as each piece was drawn in, it punched holes into Jupiter's clouds. It's noteworthy that every planet we've discussed so far has experienced impacts. Accretion is a dangerous process, and it continues to this day. Earth and Mars were whacked so hard they got moons, Venus was hit so hard she spins backwards, and Mercury was hit so hard he lost most of his crust and mantle. Jupiter is still being impacted in modern times. The lower image shows the comet falling apart in infrared just before impact. One of Jupiter's most obvious features is a hurricane-like storm called the Great Red Spot. It's called that, well, because it's a spot that's large and red. It's currently about 2 times the size of Earth, but it is shrinking. Not that long ago, it was closer to 3 times the size of Earth. This storm is rather unlike a hurricane, though, since hurricanes normally last for less than a couple of weeks. This storm has been raging on Jupiter for over 400 years. Smaller storms like these often combine to form bigger storms. sometimes even changing color as different types of materials are churned up from below. Here you see the stripes or belts of Jupiter. These stripes are caused by Jupiter's strong winds and fast rotation. Earth has similar wind patterns, but we don't see them as clearly since Earth's atmosphere is much thinner and it rotates more slowly. It takes 24 hours for Earth to rotate once, but Jupiter does it in only 10 hours. Here you see an image of Jupiter's ring. It can only be seen when the spacecraft photographing it is behind Jupiter and the sun is hidden behind the planet. You can see how thin the ring is compared to the large planet. In this cross-section of Jupiter's rings, we see 4 moons that orbit within it. Here, 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 and here. Like the moons, Jupiter's rings are made of rocky material that reflects very little light, which is why we can only see the ring from behind the planet or in infrared wavelengths. The Galileo probe was dropped into Jupiter years ago to take measurements of Jupiter's atmosphere. Currently in orbit around Jupiter is a solar-powered spacecraft called Juno. We are unsure how long Juno will last, as its orbit takes it dangerously close to Jupiter and in a very strong part of Jupiter's magnetic field during part of its orbit. Here are some recent photos taken by Juno. The first image shows one of the polar areas, and the other images show the roiling clouds in the mid-latitudes. These images, taken with a different instrument on Juno, show many strange spinning storms interacting with one another. Both of the Voyager spacecraft launched in 1977 visited Jupiter. Voyager 1 went past both Jupiter and Saturn. Voyager 2 flew past all 4 of the outer planets. Both spacecraft are far beyond most of the Kuiper Belt where Pluto lives and are beyond the area where the sun's gravitational effect influences them. At the time of this recording, Voyager 1 is about 167 AUs from the sun, while Voyager 2 is 139 AUs from the sun. As a comparison, Pluto is only 40 AUs from the sun. The link at the bottom of the PowerPoint will show you updated versions of these numbers if you wish to check it out. Saturn is the planet with the most extensive ring system, though all 4 of the outer planets have rings. Here you see an image where the sun must be off to the right. The lit half of Saturn is to the right, and the planet is casting a shadow over the part of the rings that lies to the left. Saturn, like Jupiter, has only a 10-hour day. Because of this fast rotation, both planets are oblate, or fatter across the equatorial diameter than through the polar diameter. Here, you see several pictures of Saturn and its rings. At different times during Saturn's rings, you can see the rings at different angles. Sometimes they are easily seen, as they are in the top image. At other times, they are more edge-on and appear much thinner. Saturn's rings are so much more visible than Jupiter's, not because of size, but because they are made almost entirely of ice. And ice is much more reflective than rocky material. Also like Jupiter, Saturn is composed mainly of hydrogen and helium, the 2 lightest elements. Saturn also has some nitrogen in its atmosphere. Saturn, though, is less dense than Jupiter. In fact, its density is so low that if there were a bathtub big enough, Saturn would float in it. Saturn is unique among the planets in having a density less than water. It has around 200 confirmed moons. Notice here that the south pole of Saturn is darker than the northern half. Saturn is a large planet, but its rings make it even wider. The image you see is to scale. If you could pick up and move Saturn to our part of the solar system, Saturn would take up almost all the space between the Earth and the Moon, though it would wreak havoc on our ocean tides. Both of the Voyager probes launched in 1977 passed by Saturn, and the Cassini mission launched in 1997 had Saturn as its target. The Cassini mission ended in September of 2017. Cassini's job was not only to study Saturn itself, but also its rings and its moons. In the last lecture, we discussed Enceladus, which was found to have geysers erupting water into space from its surface. Cassini also observed wave action in Saturn's ring particles as moons revolved around the planet, and even found the lakes on Saturn's moon, Titan. Saturn's magnetic field and atmosphere react to solar activity by producing aurora, similar to Earth's northern lights. To have aurora, a planet must have both a magnetic field and an atmosphere, and all four gas giants have both. We see the aurora best on Saturn. Jupiter isn't tilted enough to see the polar regions well, and Uranus and Neptune are so far away, they're difficult to spot. Here is a close-up image of Saturn's rings taken by Cassini. The rings are made of boulder-sized chunks of rock down to sand-sized grains of rock and ice. The ice is highly reflective, and that's why Saturn's rings are so easily visible from Earth, even from such a great distance away. The rings are incredibly thin, and the pieces of material in the rings are constantly moving, disrupted by both Saturn's gravity and that of several small moons that orbit within the rings. Here you see a cross-section of the rings. Different parts of the rings are named by capital letters. A ring was discovered first, followed by B ring, etc. In the lower image, you can see the same thing from a different angle. Notice the gaps that you see between some of the rings. There are moons that orbit within these gaps. The largest gap, called the Cassini division, is named for the astronomer that discovered it. The Cassini spacecraft was also named for him. Here is an image of Saturn in infrared light. Notice how much more the rings glow than the disk of the planet itself. Ice reflects not only visible light, but infrared light as well, making them so much brighter. This image shows a size scale model of the moons in the top image. Notice how much larger Titan is as compared to the rest of the moons. The lower image shows Saturn and its moons to scale by distance. Notice the lists and arrows to the right, indicating that those moons don't fit on the screen on this scale. Notice that the geyser-producing Enceladus is the source of the material for the E-ring. Farther outward, we have aqua-colored Uranus and one of its moons, Ariel. And yes, you pronounce it Uranus, not Uranus. Uranus, along with Neptune, is considered an ice giant, though they are both also considered gas giants. Notice how large they are compared to the Earth. Though both these planets are made of materials that would be gases on Earth, they are so cold because they are so far away from the sun that they are probably more like slushy, icy consistency than true balls of gas. Uranus and Neptune are often pictured as they are in the upper pair of images. Uranus, much paler, and Neptune, a much darker blue. In fact, they are much more similar in appearance to each other than those images suggest. The Neptune images were taken by Voyager 2, used different filters, and were processed differently to bring out some of the dark spots and streaks that we see on its surface. In reality, the two planets appear almost identical. When using the same filters and processing techniques, they appear as the bottom pair of images, both pale aqua. Like Jupiter and Saturn, Uranus is mostly hydrogen and helium, but its bluish-green color comes from methane also found in its atmosphere. Uranus is nearly featureless, meaning that it doesn't have the storms, the stripes, cloud formations often seen on the other gas giants. Its tilt is so extreme, over 90 degrees, that it looks like it somersaults rather than spins. It takes 84 years for the planet to revolve around the sun, meaning that each season is 21 years long. If you're about 21 years old, that means you're only one season old on Uranus. If you had been born on the first day of winter, it would still be winter. Here, you can also see Uranus's rings. They appear vertical rather than horizontal due to the extreme tilt of the rotational axis. It's likely that Uranus is sideways because it was hit by something early on in its formation that knocked it sideways. Uranus's rings are extremely thin and very dark. This means that they are very difficult to see, and we are unable to see the rings from Earth. Like Jupiter's, Uranus's rings are made of rocky material. Here you see several of Uranus's moons. They revolve in the same plane as the ring system. The largest of the nearly 30 moons are shown, each named for a Shakespearean character. Uranus was the first planet found in modern times. 1781 might not seem modern, but all the other planets we've discussed already were all known to ancient people. Uranus is so distant that it couldn't be discovered until after the invention of the telescope. It was discovered by an astronomer named William Herschel, who worked for King George. Herschel wanted to name the planet George in his honor, but that name was rejected. Wouldn't it be weird to have Mercury, Venus, Earth, Mars, Jupiter, Saturn, and George? And the final major planet in our solar system is Neptune. Neptune is very similar to Uranus in size, but again is usually pictured slightly more blue. It often shows streaks of white clouds and darker stormy areas. Here you see an image of Neptune's rings. Like Uranus, Neptune's rings are very dark and reflect very little light. They can only be seen when the brightness of both the sun and the planet are blacked out. Neptune was actually predicted to exist before it was discovered. Remember, Uranus had been discovered in 1781, and over the years, people were studying Uranus and its orbit. It was discovered that Uranus was not traveling as quickly as it ought to, meaning that something large must be out there beyond Uranus, affecting its orbital rate. In 1846, calculations were done to determine where and how big this object had to be, and Neptune was found just a few months later. Similar to Uranus, Neptune is mostly hydrogen and helium with some methane that makes it blue. Though Uranus is rather featureless due to chemical reactions that create haze in its atmosphere, but Neptune doesn't have this. As it is 30 AUs from the sun, Neptune is 30 times farther from the sun than Earth, so the chemical reactions that cause the haze on Uranus aren't present at Neptune, so we see more features in the clouds. Neptune is so far away from the sun that it takes 165 years for it to complete its orbit around the sun. In 2011, we celebrated the 165th anniversary of Neptune's discovery, meaning that we've only known about Neptune for just over one Neptunian year. We also see patterns in the activity of Neptune's atmosphere. Sometimes there are more storms than others. While Neptune is the outermost planet, Pluto is beyond it. Well, usually. Pluto's orbital period is 248 Earth years, but its orbit is more elliptical than Neptune's. So for 20 years out of its 248-year period, it's actually closer to the sun than Neptune, and their orbits do cross in two places. But though their orbits cross, Pluto and Neptune will never collide. They are in a 2 to 3 orbital resonance. That means for every 2 times that Pluto orbits the Sun, Neptune goes around exactly 3 times. So they will never be at the same spot at the same time. Much like Jupiter's Great Red Spot, Neptune had a Great Dark Spot. This hurricane-like storm was about the size of Earth. Jupiter's spot has existed for over 400 years, but Neptune's spots come and go, forming and later dissipating. Neptune is a very stormy place, mostly due to the fact that it has winds that blow up to 1,600 miles per hour. You couldn't walk on Neptune, not only because it's made of gas, but also because you couldn't stand up in the strong winds. Here's another image of the Great Dark Spot on the left. In the image on the right, the Great Dark Spot is the largest spot on the left. A smaller spot called Scooter is below it, and even farther south is another dark spot called Dark Spot 2. Each storm on Neptune travels at different speeds, so they were close together at the time of this image, but they wouldn't always be so. And here's an image of Neptune's rings. They may have been formed from a moon that was torn apart, meaning that these rings may not last very long as compared to the age of the solar system. Finally, as with the inner planets, the outer planets are named for gods. Jupiter is the head of the Roman gods. Zeus is his Greek equivalent. He is the most important god in both mythologies, so it's fitting that he shares his name with the most massive planet. Saturn is Jupiter's father. He was the Roman god of agriculture. Kronos is his Greek counterpart. Uranus is the Greek god of the sky, and planet Uranus is the only planet named for a Greek god rather than a Roman one. His name in Roman mythology is Caelus. Neptune is the Roman god of the sea. Poseidon is the Greek version. Each planet's symbols are also shown here. Again, you don't need to memorize them, but you may see them on sky maps or other illustrations related to the planets.